Okay, so in our next lesson today, we're going to look at communication and matrices, mainly communication matrices. So you'll see we often, we'll just give it a symbol like that. We'll use C often to say the first communication matrix. So what a communication matrix is firstly it's a binary matrix. If you don't know what a binary matrix, it just means it only has ones and zeros. So binary coding is used in computer coding because you have one and zeros and things like that. So you don't need to worry too much, but a binary means ones and zeros. So what a communication network shows is a way how things are connected to each other. And often we can use it as like literally someone can talk to someone, actual communication, or it could be things like a machine can go to that machine or, things like that. All right, so let's have a look. We're going to look at an example where it's people. So say for some reason it says a social network. So maybe, who talks to who. All right, so when we're setting up a communication matrix, first we look at how many people or how many things we've got. So if you look here, we have 1, 2, 3, 4. So our communication matrix, our first, is going to be a 4x4 because we had 4 people. Okay, so this is going to be known as what we call our first step communication. So it's exactly what's happening and who communicates with who. Okay, so we're going to do a 4x4. So what we're going to set up with is we're going to have 4 rows and 4 columns. So we might have Vicky, Kathy, Stephen and Paul. And then because I've done that order that way, I've got to go the same way. Vicky, Kathy, Stephen and Paul. Okay? So whatever way you write it out, it's got to be the same. So see how it went that way? That it's got to go the same order that way. Okay, so what happens is if they can communicate with each other, there's a number 1. If they don't communicate with each other, we put a 0. So often we're not going to, the person won't communicate with themselves. So say V to V is going to be a 0. And if you looked at it, these spots down here, this would be K to K. So there would also be 0. So what you find is there's zeros on what if you remember back, we called that the leading diagonal. Yeah? So that was called the leading diagonal. So we'll see, because you don't communicate with yourself, there's zeros along there. Okay, now we're going to look at between. So I'm going to go across this way. So can Vicky directly talk to Kathy? Now, can you see the 2 arrows are going either way? So we'll put a 1. Yes, they can. Can Vicky talk to Stephen? Yes. Can Vicky directly talk to Paul? No, so there's a 0. Kathy can talk to Vicky. Kathy can talk to Stephen, and Kathy can also talk to Paul. So there we go. Stephen can talk to Vicky. Stephen can talk to Kathy and can also talk to Paul. So there's ones there. And the last one, Paul can't directly talk to Vicky, can directly talk to Kathy and Stephen. Okay, so here we are. We have set up, that's the 1-step communication matrix. So once you've got the 1-step communication matrix, we can then use that to find other things. Okay, so we're going to do another one. And now someone said, we did a little bit of this at the start with, remember, the towns and they're connecting. The only difference with this is we're only going to have a 1 and 0 at the start between the communication. So there's only going to be 1s and 0s, a direct. There wouldn't be more than one path. Okay, let's have a look at this one. We've got another set of people and they can speak different. They're in a backpackers hostel and they can all speak different languages, and here's how it's set up. So I'm going to pause the video for a sec let's see if you guys can set up the one-step communication matrix using this diagram. So this is the diagram. Use that diagram and set up this down here, the one-step communication matrix. All right, so let's go through this. So Eva will not talk to herself, but Eva can talk to Wong, but cannot directly talk to Yummy and Kim. So Wong can talk to Eva, won't talk to themselves, and then also Wong can talk to Yummy and Kim. Yummy cannot talk to Eva, can talk to Wong, won't talk to themselves, and can't talk to Kim. Kim cannot talk to Eva, can talk to Wong, can't talk to that, and like that. So is that what everyone got? Yes. And we can see that there's zeros down our leading diagonal. Okay, so what we just looked at then when we did the direct who could talk with who was the one-step communication. So what we can say now, what we're going to do is we're going to look at two-step communication. And what two-step communication is if you can get a message to someone through something else, so someone else. So it's like you give a message to the first person and then they pass it on. So if you have a look here, if we did like here, we've got Eva. If she wants to get a message to Kim, can you see that she does it in 1, 2? So there's the two-step communication method. So Eva can get a message to Kim via 2 steps, but there's only one option for her to do that, isn't there? There's no other person Eva could talk to get a message to Thing. So here, what I just did there, that is a 2-step communication. So sometimes we want to know how many 2-step communication methods there are. And if you look down here, this is the 2-step communication matrix already done up for you. We should see a 1 between Eva and Kim, and you can see it here, and that was that one method of using 2 steps to get a message, okay? So how we can quickly get the 2-step communication matrix is by getting the first our first communication matrix. So we would have set this one up, which we did, and if we want to get this one down here, all we have to do is square it. So you remember we've done a little bit, raise it to the power of 2, and you'll end up with this 2-step communication matrix. So we just have another look at just one of the others. So if we look at I'm going to look at this one. This is between Yummy and Wong. They reckon there's one 2-step communication. So can you see, if I go to Yummy, she could get... There's a 2-step communication where I go get a message to Wong. So you could go like this, 1... Oh, wait a minute, stop that. All right, with this one here, you know how we had the leading diagonal before? Here down, if we go down the leading diagonal, these ones are what we call a redundant link. They're not redundant. Oh, can't spell. What it means is, there's 3 options where Wong can talk to someone else and then it'll go back to the Wong, which is why would you want to send a message that comes back to yourself? So that's why we call it redundant. But there's 3 2-step options, and it makes sense because here they are. You go like you go, here's the 3 steps. There's one here. Do you want to go sit over there? Over there. Yeah, Ta. Next to Jerome. Thank you. Boys, shh, listening. So the 3 here, this 3 2-step communications is this. There's 1, he goes that step, 2. There's one of them. Here's another one, 1, 2. It goes back to himself, yeah? 1, 2. There's the two-step communications between Wong and himself, okay? But we don't need to look at them because they're like that. All right, let's start this one. So we just said the redundant link. So a communication link is said to be redundant if the sender and the receiver are the same. So if it's going back to yourself, the same person, it's redundant. So all the non-zero elements in the leading diagonal of a communication matrix or its powers, so because we saw it in C2, they're redundant. Okay, so let's have a look at this little example down here. It says how many two-step communications links shown in this matrix are redundant. So all we're going to do is count up those ones in that leading diagonal. So it'd be 1 plus 2 plus 2 plus 1. So how many are redundant? 6. So the matrix below shows 5 people, Alan, Bevan, Charlie, Drew and Isa, can communicate with each other. A 1 in the matrix shows that the person named in that row can send a message directly to the person named in this column. So that's the case with all communications. They're going to tell you that in an exam just so that it's clear the rule is set. So for example, and they'll give you an example, 1 in row 3 and column 4 shows Charlie can send a message to Drew. Okay, Isa wants to send a message to Bevan. Which one of the following shows the order of people through which the message is sent? So here's Isa. She wants to send a message and she wants to get it to B. But if you look along, along here, who can Isa send it to? She can only directly talk to who? Charlie. All right, so we're on Charlie now. So we've gone Isa and now we're on Charlie. So now we're on Charlie, but we're trying to get to B. But can Charlie talk to B? No. So not going to go back to Isa. So who are they going to go to? Drew. Good. So we're going to go to here, Drew. So now we're on Drew. So we go down to Drew. Can Drew go to... Who do we want to get to? Oh yeah, so Drew can go to Alan. So it goes to Alan, and then we're on Alan, and Alan can go to Bevan. So where's that one? That is E. Okay. So we're also now going to look at an identity matrix. So an identity matrix has 1s down that leading diagonal. So we can see here it is, and has 0s everywhere else. Now an identity matrix, it's sort of like a number, it's like a number 1 in matrices. In terms of if you multiply something by a identity matrix, you get the same thing. Because if in maths, if you multiply something by 1, you get the same thing, don't you? So if you go 3 times 1, you get 3 again. So here, if you multiply a matrix, so you can see down here we're multiplying matrix A, there's A. If we multiply it by a identity matrix, which is here, we end up with the same thing, okay? So that's what we need to know. Now we also need to know that the identity, it's a square matrix, isn't it? Yeah? So the I is a square matrix. What does that mean? It's got the same rows and columns, so that one's a 3 by 3. Okay, now another matrix we're going to need to do with some of our problem solving is going to be called an inverse matrix. So an inverse matrix, so we could write, if we have matrix A, then the inverse is A to the power of -1. That's what an inverse is. Now, if you have in normal maths or something, if you have a number, if you have 3, say, to the power of -1, what that actually can be written like this is 1 over 3. So that's sort of like dividing, isn't it? If I was to times something by the inverse, it's like I'm dividing by that number. So the inverse, and you might want to make a note, it's the way we divide in matrices. So if you ever need to divide something when you're problem solving, you're going to times it by the inverse. So we can't actually do a division, so we use the inverse. So we have to learn how to find the inverse, and we have to know how to do it manually just for a 2 by 2. So can you see down here, my little matrix A is a 2 by 2, isn't it? So you only have to know how to manually, like physically work it out for a 2 by 2. So you can see here we've got matrix A, and it has 4 elements there, A, B and C. If you're going to find the inverse, what you're going to do is you're going to do this to the matrix. So what you have out here is this bit here. You're going to times the number A and D together, and you're going to subtract if you times those two together. So that's what you're going to do outside. And this bit, so this will end up being like a scalar number. And then if you notice, these two get swapped around, and these ones become negative. So we'll do it, don't worry, when we do an example, it'll make sense. So there's the formula to find the inverse. Now, what this bit down here is called, that little bit there, is called the determinant. So it also has its special name. So we can first find the determinant, and then we'll find the inverse. Let's go do some practices, and it'll make it a little bit, but you've got this in your notes. All right, so up here, here's an example. So this would be, if I asked you to find the determinant, so the determinant of, I'm going to say matrix H. So sometimes they'll just write DET, okay? Now the rule is, so remember they were given those positions. So the actual general rule is A times D minus B times C. So if I was doing it for H, A is 2 and D is 3. And then I'd minus B times C. Okay? So then you can actually do those numbers, which is 6 minus 8. So my determinant is negative 2. Okay? So if I was asked to find the determinant of H manually, there we go, we've got that. Now, if I'm asked to find the inverse of H, so we could write it like that, or I might just say find H, I might write negative 1, the inverse. So the rule actually is 1 over AD minus BC. Then we flip those two and we make these ones negative. Okay, so in this example, now we said that this bit on the bottom is actually the determinant. So I've already worked that out. This is the determinant. So I don't need to go calculate that bit. I've already done that. So I'm going to say 1 over negative 2. That's what my determinant was. Now, I'm going to swap these numbers. So these two are getting swapped. So 3 is going to be up here and 2 is going to be down there. I'm going to make these other ones just stay the same spot but become negative. Okay, what did we do when we had a scalar number out the front of a matrix? What happened? We times it, good. So what I'm going to keep going, and I'm going to times all the numbers inside by negative 1/2. So it ends up being 3 over negative 2, negative 4 over negative 2. All right, someone got a bit lost there, so what I'm doing is I'm doing 1/2 times the 3, 1/2 times the negative 4, 1/2 times the negative 2, and the negative 1/2 times 2. Oops. So that And if we tidy that up, we end up with 3 over negative 2, negative 4 over negative 2. And what's a negative over a negative, boys? Positive. So this will, sorry, I've run out of room here, will simplify to, we can't fix that one. This one will become positive 2. This one will become positive 1. And this one will become positive 1 as well. Okay, mainly you need to know just how to set to here, because you always will have your calculator, so you can do the little step by on the calculator. Now, I'm going to pause it there. We're all going to do these on our calculator.